Hey, what's going on, guys? Coming in here. In this video we're going to be writing an assembler that is going to be converting this like mnemonics into the binary executable file. It's supposed to be running under our 8-bit breadboard computer emulator, the computer that was originally built by emulator. So our goal is to convert this sort of mnemonics into the bytes, so that eventually this assembler file would get converted into this like binary file. So I think that it's reasonable to kickstart with expecting the contents of the binary file. So I'm using XXD on Linux. This is simply a hex editor, so you can use whatever hex editor you like. And I'm going to programs and add bin, and here we go. So we have 1 byte, another byte, and so on and so on. And you might be wondering, like, what the heck are all of these numbers? Well, if you have been following the series on creating the breadboards, the Banner's 8-bit breadboard computer emulator, then it should already be pretty clear for you, like what exactly this goes. So for those who hasn't been following that, I just want to remind that every instruction in Banner's computer consists of 2 parts. So the mnemonics takes the upper 4 bits, and the argument, if available, it takes the lower 4 bits. So here, for instance, we have the opcode, and here we have argument. And based on this knowledge, we can already kind of sort of make some hand disassembling for this guy. So 1-8, this means that opcode is 1 and the argument is 8. So here we have the list of opcodes. So 1 is LDA. This loads the contents of the memory address stored in the argument into the A register. So in this case, we have LDA A8, and here indeed we have 1, which stands for LDA, and we're gonna be loading the value, whatever value we have at the random access memory, indexed by 8, and that would be the value of stored into the A register, and so on. And same applies for the rest of this kind of opcode. So 2 stands for add, and we see it here, and then 9. So 2 stands for opcode add. Here it is. So add 0010. This is 2. So this is binary, but in decimal this is 2, right? And then the argument is 9, and here it is. So this means that later on we take the content and the memory address indexed by the argument, which is 9. In our case, and storing this into the B register, and then performs A plus B and stores the value into the A register. So that's pretty much all about it. So we already have implemented this logic to like handle these opcodes, handle all these instructions. But but currently, if we actually want to write a new program, then the only way, so we can either source the existing binary files that we have been doing in the previous video, or alternatively, if we want to write our own program, we need to put the program here, just writing the source code of the breadboard computer emulator itself, which is not really handy. So assembler is a program that is going to be taking this like text file containing mnemonics built from the instruction followed by the argument if available, and turn this into the bytes that later on are appended one to another, forming this sort of a binary file at the very end. So hope it's more or less clear at the moment. And now, without further ado, let's actually start writing some code. So I think that we can take this particular mnemonics as well. Actually, it doesn't really matter that much which one in particular we take. Well, anyway, so here, so I just want to define assembler for Banner's breadboard computer, and yeah, here we go. here we go. So let's actually start by opening ASM file, assembly like source code file, I'll later wrap this into some functions if needed, but for now I just want the bare logic. So let's say with open, and so what kind of file name we want to, well, for now let's just call it task.asm. Later we'll provide logic to use the command line arguments, I believe. And we want to read the bytes. This is essential. No, sorry. We want just to read. No, it's ASCII. It's not binary. So as file. And for instance, yeah, I would probably, yeah. Hold on a sec. So probably here in the programs, I just take this code, this away, cut, and I rename this to binary, and also create the ASM folder. And put it here. I'm not going to be using this because they are a bit too sophisticated, but add should be fairly enough, so I don't need this one. In here I want to create my own new one called task.asm. Okay, and so here ASM, let's start by actually reading a.asm, and let's print f.read. So at the moment, so Python 3 asm.py, we should see the content of the file. And here we go. So here is the content of the file. So far so good. So I don't know, yeah, probably we can start, I'm not sure whether we should start from this one or, yeah, let's probably drop it. I don't want this. Or yeah, we can actually yeah, we can save it for the later tests, right? But for now we nope. Oh yeah, so still alive. All right. Okay, so let's go here and let's say LDA and 0x 05, for instance. I want the hexadecimal types. Well, actually, binary should like decimal should also work. So yeah, let's go for. We don't need breadboard, and we don't need the README. Okay, so make sure. Yeah, so we've just opened our file. And now, what we also want to make sure that we do take into account the stripping the commentaries. So let's have 0f, for instance, comment 2, and say nope. Okay, just want to have the lines with and without the commentaries. So now we need to loop over mnemonics, over source lines. So for line in f.read, and I want to split it by, oh sorry, what have I done? f.read split by the new one character, and print the line and whatever we have. Let's have a look. Okay. Excuse me. So what? Oh, colon. Okay, so yeah. So let's say we want to skip the lines if so if line is not equal to, so if line is not equal to empty one. All right, so now we have only those lines. Great. Now let's try to say line dot split by the semicolon and the verb first. Okay, so we do strip the commentaries. So yeah, let's go for this. So first we want to strip the comments, and let's say, so how we call this variable? Let's call it instruction. Let's call it instruction equals to this, and let's print the instruction, right? Okay, yeah, we got it. So then we need to figure out the length of the instructions. So length, so this is gonna be okay, just counts all. So split by empty space. Okay, so whoa. Yeah, let's first what the hell is that? I'm wondering. Yeah, didn't I shouldn't specify the white space there. Yeah, probably just oh no, not the line, but yeah, instruction. Oh no, sorry. No, actually, okay, like this. Okay, so so let's call it instruction length is equal to this one. Now there would be two cases. So here we want to get instruction length, and now we have two cases. So the 2 versus 1 element. So opcode, the single opcode versus opcode plus the argument. So I want to say that actually this is the matter of, yeah, that's probably first let's go for extracting the opcode. So extract opcode, and opcode would be, so we're going to be using the lookup table here. So we can say opcode is going to be equal instruction 0, and we want to say opcodes indexed by this sort of a thing. Okay, so now it's time to define the instructions. So instruction set, and we call it opcodes, and this is gonna be a dictionary, not a list, a dictionary. And here we have, so starting from nup, okay, nup is 0, then LZA is 1, okay, add is 2, sub is 3, 1, 2, 3, add sub STA LDY, STA is 4, LDI is 5. Okay, 6 jump. Unconditional jump is 0x06. Jump carry 0x07, and jump 0x08. So let's check those out. So jump carry 7, yeah, jump carry 7, jump 08. Out is going to be E. Out 0x0E, and halt HLT. Okay, and halt 0x0F. Okay, so now we get our opcodes. So yeah, now let's, before we go, I just want to print this up. No, it's instruction index by 0. So we have okay, so I did something horribly wrong. No, not like this. Actually, dot split like this. Okay, so here are the instructions. So far so good. And now we need to put it here like this, and now we can print the opcode basically. And here's what we have. So we have one for so here is our test program. So we have one for LDA. So far so good. Well, actually, yeah, 2 for add. So 1 for LDA, 2 for add. Then nope is 0. And yeah, 1 2 0 0. So far so good. Okay, this is great. So the next thing is the argument. So we want to extract argument if available. So here, if instruction length, so if instruction length is equal to 2, in this case, let's call it argument, is going to be equal to the second element, and otherwise argument is gonna be equal to 0. That's it. So now let's also print the argument. Yes, it would still be yeah, something goes wrong. It just yeah, I forgot to make it length actually. Okay, and nope. Oh, nope. Hold on a sec. It's all. No, length should be 2 or 1. Okay. hold on guys, just I need to wrap my mind around this. Oh man. Yeah, let's probably make it like this. Okay. And okay, and now here we put length. Okay, 2211. Yeah, now this should work. And now let's have a look at the argument. Okay, so we have either 0x05, 0x0f, or 00, which is exactly the case. But we also need to make sure that the argument is going to be the integer. So we want to say int, and now it would be printing what? Oh, integer with base 10. We need to explicitly specify the base to 16. So yeah, in this case, we're going to be using this. Okay, and if I want to make it hex, we're going to be using the hexadecimal numbers. Okay, so far so good. So now we got this hexadecimal numbers. Great. Okay, now it's time to encode the instructions. So here I say encode instruction. And let's call it program byte, and this is gonna be, we need to take the opcode, right shift this to 4, and then bitwise OR it with the argument, and that's pretty much all we need to do, I believe. So let's print the program byte. Hold on a sec. Okay, 2, 1, 4. Yeah, let's print. I just don't understand like this. I want to print in hex. Okay, 152F. Okay, 152F. So LDA is 1, and then we have 5, and this is 2, and then F. Yes, exactly the case. And then nopes. Yeah, so it seems like it's true. So finally, we want to write bytes to the file. But well, probably let's make it a little bit different. So let's say binary program, or yes, yeah, binary program. Let's call it program bin, and like this. So it's gonna be a list. Yeah, so let's probably, yeah, we can here and append instruction to binary program. So here program bin dot append and program byte, and at the very end I want to print program bin, and I use a list comprehension to print the hexadecimal values, so 4i in this. So we have the list with bytes. I just print them as hexadecimal strings. Well, literally they would be used as the integers, so they would be written as the integers to the file. Okay, so I'm wondering, do we need a class here? Probably we don't. Probably we don't. So the next thing we want to write write binary program to file. So with open, let's call it for now just hardcode, the task.bin here, and we want to write bytes. This is essential. Again, as file, this should work. So we'll redefine it, but yeah, this should work. In here, f.write, and we convert to bytes this list of program bin, and basically we are done. So this should be it. Okay, so just create a task.bin, and now if we say xxd test.bin, we have 152f00, and then just 00, because I'm not sure why exactly he prints that. Is that a matter of not sure. Okay, now let's go for a bit different test. So if I take this add ASM, here is another thing that we don't do this data. So I want this to be called the data, basically. Or okay, let's try with this first. So paste. I think the comments, the lack of comments shouldn't be a problem yet. So xxd asm, then test bin, and then xxd bin and add bin. So let's compare. So this is the original binary, and this is what we have. So far so good. And then we also need to provide this when we just initialize the data. I need to think how am I supposed to be doing that. So how can we do that? Well, I don't know. I feel like I want to make it like a data, basically. Yeah, it's on the time of encoding. So if I just make it like, if I put this guys here, it would just give me an error, because it will be trying to look, so it doesn't have this key error goes here, so it's not okay. So let's make it, we can do however we want, basically. So let's make it a data, like this. It's not really the opcode, but this should be fine. And arrow x 00. No, no, let's try to, so let's maybe try accept would work. Let's just, so since it goes here, so let's make it try and accept. It's not the best ever practice, but we're not doing best practices here. We're just trying to get the very gist of how things work, basically. So otherwise, so the let's say opcode is equal to 0, just to make sure. It does work. So this compiles. So okay, so it just gives the 0 for an opcode, but not the 0, but here we need to say like this, but the first one. Okay, and also in this case we need to specify them in like this. Okay, yeah, this could be the case. And test bin. Okay, here we go. So just want to copy the string to make sure that it just goes exactly like in the original binary. I'm not sure why the original binary actually has a bit more zeros. Oh yeah, here is another thing. So we need to we actually need to right shift them to, yeah, hold on, to make it like this. What? Oh, no, hold on a sec. Yeah, it happens. Okay, we just don't need to make this shift in case of the opcode is. So wondering, what if we make a hack of shifting this to 8? Nope. Alright, so another idea is to, if I don't do this here, and if I do it here instead, and here I just don't do it. Okay. Yeah, now it seems to be much better. Okay, so let's go for a comparison again. Copy and... Okay, yeah, exactly the same. I'm still a little bit wondering why it actually, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it probably does fill all the 16 bits with the zeros, but I think we don't really need this for our purposes. Yeah, I think we don't. So 7 plus 3 is 10, minus 2 should be 8. So this program should result in the output of 8. Let's probably just try to test it. So if this actually gives us 8 or not. So I assemble it. So here is how the binary works, and now Python 3 breadboard.py and test.bin. What? Oh, whoa. Nope. 242. Nope. Oh, hold on a sec. That's because Just to run reference. What about knobs? So after out, so 1 knob, 2 knob, 3, 4. Yeah, it seems makes sense. So LDA 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so this should be. Then it goes to 9. That's 3. And then subs 10, subs 2. It's a little bit strange. Okay, so I found an issue here. It should be 3A. 1 to the third instruction, sub 10, 3A. Oh, whoa, that's because, that's because I'm using hexadecimal. So 0x09, 0x0A, yes. And then don't need this one. And here, what have I done? Nope. Here in test. So yeah, I just 0x0A. Yeah, because I'm doing this in the hexadecimal. Now this should work. So assembling test pi, right? And breadboard test bin, and we got 8. Fantastic. So far so good. Yeah, even despite the fact that we don't actually have xxd test.bin, we don't really need to have this trailing zeros at the end. I'm not sure why that assembler had those. We don't need that really. So yeah, we got the program and it kind of works. So this is fantastic. Okay, I think the core is now ready, so we can use whatever instruction. We can specify the data by just putting the value there, what the data is. I don't know. Yeah, I actually like how the code looks. Well, I don't like how the code looks, but now with that list, maybe I just should put it to sort of a data. Okay, let's try one experiment. So use the dat opcode here. So let's make it like this, like this, like this. It's not an instruction, it's just an assembly tool, an assembly like keyword. And in this case, we do extract the opcode, and if this is equal to that, then we can say opcode right shift back. It's maybe not the most efficient thing ever, but it does make exactly the same result, which is good. So again, we go like this, and xxd task.bin. Yeah, so it works. Just pulls it back to the right. Okay, yeah, I think that should be a little bit more a little bit better than try except. Okay, so now from now on the syntax is gonna be like to specify the data, we just use this keyword, which is more looks like an assembly basically. Just this more strict now, which I like. Okay, now let's add some bells and whistles to this thing. So first, let's say how many bytes written, for instance. So print the length of program bin and bytes written to, and the file name. Yeah, we'll replace the file name soon. Okay, 11 bytes written to test.bin, good. Now the next thing, so let's import sys and let's try to get the file name. So extract file name. So file name, like want to open file names. So let's say open file is equal to, let's say read file is equal to sys.argv and 0 1 and write file 2, and I want to try this. And here accept print usage Python 3 asm.py. So let's say path to file.asm and then path to file.bin. Okay, and sys exit. Okay, so here it gives us the usage. Test bin. Yeah, no worries. Okay, so the next thing, I want to use the read file. I want to use the read file here. And I want to use the write file here and here. Now let's delete this one. And actually, we don't actually need the second one. Why do we need? So we can just use like, yeah, just the same file name is, or no, let it be like, this. So so where is the test ASM? Oh, it's in the AS, or is it? Is it? Okay, so ASM, test ASM, and for instance bin, test bin. Okay, and now I need to make sure that, yeah, test.bin comes here. Okay, so far so good. So we got the test. What else? And if we want to run this again, then here we go. Okay, so yeah guys, I think generally this is kind of it. So from now on we can use whatever whatever instruction that we have available to write data to the file. But the one last problem is probably the file might not exist actually, so like this, so file not found. So here we can say try Okay, so why does it give an error? Oh, read file. Yeah, file not found. And if we go like the normal file name, then it writes bytes, and that's it. Okay, so far so good. And probably we can print this to print the bytes themselves, and maybe do it before the message. Okay, so I think this should be just okay. So we got the bytes and 11 bytes written to, yeah, I think this is just good enough. I think this is good enough already. So yeah guys, this is it from my side. Thanks for watching. In the next video we're gonna quickly draft a disassembler so that we could read the data from the binary file and turn it into a sort of a user-friendly mnemonics. And I would also think if it's actually possible to give the commentaries as the description, like the extended description, so that it would also like have a lookup table with this kind of data. So we can just probably replace the address. So yeah, so just print something like this. Yeah, so I need to wrap my mind around that for a while, and if that works, then we will do that as well. So just for the easiness, for the ease of the understanding how the disassembly works. So the same thing, but on the country. So converting binary to mnemonics, so that it's easier to see, to know like what the binary file is all about basically. And yeah, and the assembler, I'm not sure if there is something horribly wrong with this assembler. I'll probably improve it, but for now it seems to be fairly enough to work, to write some programs, basically programs like this with the commentaries potentially, and actually write some code for this Benitor's 8-bit breadboard computer. Yeah, this is it from my side, guys. Thanks for watching. Until the next time, and take care.